This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Suppose I had a transistor. I'll just take this few seconds to do this, and then we can talk a little bit. See, are there projectors? If I had a transistor, and I said it was connected in common source configuration, what am I saying? All right. Well, what are the elements? So this is what? Gain, drain, source. Okay. All right. I love FETs, right? I hate BJTs. I don't work with BJTs, so I always work with FETs. So if I'm saying, yeah, it would be a common emitter for people that work with bipolar junction transistors. Okay. So when I'm saying common source, what do I mean? Essentially, a resistor or something at the drain, but yeah, the source is connected to ground. Okay. Now, that's going to be important later on when we talk about oscillators, and depending on what the amount of feedback that you want and the level of oscillation, you probably wouldn't want it in common source configuration. Common source is great when you're making amplifiers, not necessarily great when you're trying to build oscillators. Anyway, so the point here is you're given the scattering parameters in common source configuration. You're given the noise figures, the optimal reflection coefficient for that particular, in order to be able to retrieve that noise, and the Rn for that transistor. And we went through the process of actually deriving or determining what the maximum gain is going to be, assuming that the system was not assuming, given that the system is unilateral. And we went through the whole process of determining what the maximum gain was. We went through the process of saying, well, we wanted it to achieve a noise figure of 3.5 dB and a power gain of 16 dB. And went through the process of allocating the gain. Now, just to reiterate, in this particular example, what we did is we arbitrarily chose what the source and the load gains were going to be. The only condition there was that the source and the load were going to be less than the maximum, right? And if you're doing a design, usually the other thing that you would look at is to ensure that the gains that you've chosen and the resulting, for example, reflection coefficients didn't give you an overly large voltage standing wave ratio at either the input or the output. And essentially, we went through the process, determined. We said, like, for example, what is the gain relative to the maximum gain at the source in order to work out GS. I asked you all a question: why was I focused on GS and not GL? And you all told me that it was because the noise is only affected by the source impedance. Fantastic. And what we went through was work out the gain circles, the center and the radius for in order to be able to achieve for that particular gain circle. Right, and then what we went through is we also worked out the noise circle center and radius. And then what we did was we plotted these on this. I was getting a bit excited on a few nights ago, so I decided to download an impedance/admittance Smith chart, and we drew both the gain circle and also the noise circle for this particular configuration. And then what we said was, hey, what we want to do is work out where are we going to choose our source impedance. And what we clearly stated was, anywhere on this gain circle that is within the noise figure circle is sufficient, is appropriate, because it will achieve our gain and it will also achieve our desired noise figure. Actually, what it will do is very likely achieve a much better noise figure than the minimum that we require, which was 3.5 dB. And then what we went through the process was this, we arbitrarily, right? So this is an important point. We arbitrarily chose a point on this gain circle. I chose that point so that it gave us the lowest voltage standing wave ratio, and then what we went through the process of working out what was the network that would allow us to transform the 50 ohm generator source into the impedance that I require in order to be able to achieve the source impedance that allows me to achieve both the noise figure and the specified gain. All right. So we were all excited because it gave us the capability now to actually design both, a low noise amplifier or an amplifier which had both the desired gain characteristics and the noise characteristics. Now, what I'll do in this lecture, what we'll start off with, is start talking about the minimum noise amplifier. Okay, so what we've talked about in the previous few minutes, as a recap to our previous lecture, was essentially, hey, somebody told us, let's achieve this particular noise characteristic, or we want we want our noise figure to be less than a particular value. What we're going to do here is, suppose someone said to you, well, you're building some radio astronomy piece of equipment and you want the absolute minimum noise figure, right? Now, what we're going to do is go through the process of being able to do that. Now, as I was talking to one of your colleagues, as we were coming into the room, he was like, why did you introduce this concept of equivalent temperature, right? That was the question. Why did you introduce this concept of equivalent temperature? And what is its significance, and what can I use it for other than maybe do some trivial calculations on what is the noise power for this power amplifier, or this amplifier. And one of the things that I did say, and it's just a little bit of interesting bit of information, if you've got the equivalent temperature, that also means that if you cool that device down, right, you can also reduce its equivalent temperature, noise temperature, so therefore you can actually decrease its noise figure. So that's another thing that you've got up your sleeve if you really needed to reduce the noise figure of a device, right? Anyway, as an aside, I always find these things exciting. Hopefully you all do also. All right, so the question was, or the problem that we've posed is design a minimum noise figure amplifier. And again, we're given the scattering parameters, and we're given these scattering parameters in common source configuration, right? Unless somebody tells you otherwise, you should assume it's common source configuration, right? When you're looking at data sheets, that's a standard of how people present the scattering parameters. Now, okay, question. What are all these values? Just making sure that nobody's forgotten. What's this one? All right, perfect. Okay, S11, S12, S21, S22, perfect. So the very first thing that we're going to do is we're going to check the stability, and essentially what we go through is, and show that this system's actually unconditionally stable. And once we go through that process, we can actually do. What that allows us to do is, if we know that it's unconditionally stable, it allows us to, if we were going for maximum gain, what does it allow us to do? If we were trying to achieve maximum gain, let's forget about the noise figure. If we were trying to do maximum gain, what would we do? Okay, conjugate match, right? So here, what we're going to do in order to get the maximum gain is we're going to do a biconjugate match on the load side, but we're not going to do it on the source side. Why not? Okay, you mentioned it to me a few seconds ago. I asked you and you told me the answer. Can you repeat the answer? Yeah, okay, so if we want the maximum gain, right, and we can do a conjugate match on the load. We know that that's going to give us the maximum gain. right? And it has no contribution to the noise figure, right? So now so we've separated the problem. We've said we know the transistor gain, right? And it's going to be related to S21. We know S21 squared. We know what the conditions for maximum, if we were free to choose our load, the one that would give us the maximum gain at the load. So we might as well choose the conjugate match at the load. But we can't do that at the source because we know if we chose the biconjugate match at the source, it would very likely give us a terrible noise figure, right? And we did an example, I can't find the slides, but we did an example where we showed, if we did that, we got a very large noise figure. So now let's look at what happens in order to work out the minimum noise figure, right? So we said, well, we can do a biconjugate match at the load, so we can get that. So we also know that the source, the optimal reflection coefficient in order to be able to achieve the minimum noise figure is given to us, right? The manufacturer actually gives us to us, and I've left this out. I should have said gamma opt equals 0.47, 65 degrees, sorry. And there'll be an Rn here also, and the noise figure. Okay. So what we're going to do now is actually work out the source impedance. So what we're able to do is go through the process, and hopefully I haven't mixed up the slides, but essentially what we do is we plot our gamma S, which in this particular case is 0.475 minus 65 degrees. We've discussed many times on how to do that using our compass, right? And I won't go through it, but essentially all you do is you draw your point gamma S, and we said if you want to work out what the matching network or the network which transforms the 50 ohms to your desired value, what we do is we've got gamma S, we go down, in this particular case, the curve of shunt capacitance, so we know what the value of our shunt capacitance is. Then we'll add a little bit of inductance, and we get to the desired point. And we can actually work out what these values are. Gamma L, we've worked it out because based on this value, you can actually also do the same thing in order to work that out. Okay? So this particular device will actually give you the minimum noise figure, right? So the absolute minimum, you can't do any better than this if you follow this approach, right? So for the given biasing conditions, and for the noise characteristics of that transistor, this is the device which will give you, or the configuration of input and output matching networks, which will give you the highest gain and the minimum noise. You can't do any better. Okay? All right, now what you can do as part of this process, maybe as a homework exercise, actually work out what the actual noise is, right? You've got all the formulae there. I should have given you, maybe I haven't given you Rn, so you might not be able to do that, but you go through that process, you can actually work out what you would expect the noise to be. Okay, so so if I ask you, hey, can you build me an amplifier which has maximum gain and minimum noise figure, or the minimum noise figure amplifier, this is a process that you would follow. Okay, excellent. All right, now what I'll do in the next slide is take you back a little bit in the sense that our designs, or our process in designing a lot of these circuits, has been focused around using a scattering parameter approach. But if you're trying to design low noise amplifiers using MOSFETs, there's a trick, right, that you can also use that gives you the minimum, matches the gain and matches the impedance and also gives you a minimum noise figure, right? And that has some advantages. If you're using, of course, if you're using MOSFETs, it has some advantages when you're using some time domain analysis tools in order to do your simulation, right? Because usually it's hard, trying to do a mixed simulation using scattering parameters and in time domain, it gets a little bit complicated, right? But if you've got a MOSFET, you can do a little bit of a trick, which I'll show you, which you should have in your bag, in your arsenal, right? So to make sure that you can use it if you're doing some, MOSFET low noise amplifier design. And the trick is as follows, right? The first trick is to say, well, I'm going to do my small signal model for a MOSFET. And you've all seen this before, right? This is your standard Ebers model, low frequency model for a FET. Can anyone tell me what all the elements of this MOSFET are, or this model are? What's this? I know it's a capacitor, right? Good. Sorry? The gate capacitance. Okay. What's this GM? This current source GM. Okay. And what? Yes, it's transconductance. GM is transconductance. And what's this current source doing?
Voltage control current source.
Yes.
And convert the input voltage to output current.
Sure. Okay. All right. So you've all seen this before?
Yeah.
Yes, you must have seen this hundreds of times before, right? Okay, good. Now, you've probably also seen that, as you're going up in frequencies, usually you've got a whole bunch of other capacitances there. Usually you've got your gate to drain capacitance, you've got your drain to source capacitance, usually you've got an output resistance. What's output resistance? Here, where I've got an RO here, where does that come from? I don't have it here. I'm assuming that RO or the output impedance is infinite. But where does it come from in practice? When it's not infinite. Come on, guys, you're losing your jobs at AMD. Yes, channel length modulation. All right, good. All right. Now, so what we're doing here is, if you look at this, you can actually look, when you look at it, because it's purely capacitive and in most cases, it's really hard to match this, right? So when you're trying to do your standard scattering approach, scattering parameter design, it can be a little bit difficult. So, but let's now start using a little bit of a trick, which is, let's look at what is the input impedance, to this particular network, right? So essentially, all I've done here is I've put just for everyone's benefit, in the source I've put an inductance, and I've also put an inductance here in the gate. And essentially what I've gone through is actually trying to go through the process of working out what is my input impedance for this particular network. Sorry. Now, how would you work out the input impedance for that network? Has anyone gone through the process of working out what the input impedance is to a FET? I'm sure you've done that, right? All right. So how would you do it in this particular network? What would be the process? Okay. As a hint, what you do is you want to work out. So input impedance is actually, Z is equal to V in on I in, right? And in order to be able to work that out, what you do is essentially say, well, rather than trying to put a voltage and work out the current, what you say is, let's assume there's a current I. Right? We've injected a current I. Let's work out what the equivalent voltage is going to be at this particular node. And you can go through it very quickly, and what you're able to show is that your total impedance this formulae. All right, yep. Okay, so all I've done, right, just for everyone's benefit, I've said this voltage is V, and then if I work out what VGS is, I can work out what GM is. So if I some of the currents here, and you can actually work it out, right? So because this is a current source, what does that also mean? That none of that current that you're putting in through IN, all of it has to be sunk through here, right? So for the current here, it's going to be IN plus GM VGS. That's another hint in order to help you go through the process of working out the input impedance, or working out the transfer function characteristic. So once you do that, what you've actually got is that the total impedance, or the total input impedance, is a real part, right, which depends on the transconductance and the ratio of the source to the gate capacitance, plus an imaginary bit which depends on the source and gate inductance, which we've added in this particular case. We've actually added these two elements, right? So we've added those two elements, and we've now got an imaginary component, right? So we've got a real plus an imaginary component. Now, what you're able to do, since you've got two variables, two equations in two variables, is you can actually choose your LS and LG to do what? If I'm trying to match it to 50 ohms, what do I want? I want the real part to be equal to? Okay, so I want this bit to equal 50. And I want this bit to be equal to what? Okay, right? So you can do that, right? So you can actually choose those values so that this value, you resonate this thing out, so if that equals to 0, and you can also, at your frequency of interest, at the frequency of interest, this becomes 0, but you can also make this equal to 50 ohms. Right? So what you can actually show is that doing this source degeneration type approach when you're designing MOSFETs or MOSFET LNAs gives you actually the minimum noise figure. So this is one of the tricks that you can actually do when you're building MOSFET LNAs. Right? So all you do is, you could, add, the source and your gate inductance in order to be able to do this. Now, let me ask a question. All right. What's the source impedance there? Suppose it's low frequency. Right? 50 ohms, right? Roughly, because this is, CGS, it's a capacitor, and if it's low frequency, you can say, well, it's almost infinity, right? As an example. This is one way that you can actually get 50 ohms. Why don't you do it? Why don't we do it this particular way? Why did I go through the trouble of trying to add, and this will always be 50 ohms real, so it'll be a very broadband match, right, as an example. Why don't you do it this way? Okay, what do we know about resistors? Right? So therefore, if you do this, you're adding noise to the first stage, right? So therefore, you don't do that. Okay. All right, and you can actually work out, and so therefore you can work out what your voltage is, and because then that noise, essentially what you're doing is you're generating noise and you're amplifying it, right? So therefore it's a bad situation, so don't do that. All right, so we now know how to design low noise amplifiers, and then also if we got MOSFETs, if you're a CMOS engineer and you're designing high frequency FETs, also shown you, at least a first order approximation, how to design those, the first stage of your LNA in order to have both a 50 ohm matched input and also minimum noise figure. Okay? And then what you would do after that is you would try to match your output impedance in the next stage in order to have gain, etc., etc., etc. Okay, excitement continues now. All right, we're going to start talking about oscillators. Who knows what an oscillator is? What does it mean? It generates an AC signal. Okay, all right, it generates an AC signal. My lecture's so boring, I've made your friend go to sleep. All right, generates a sinusoid, or you can think of it as a device which converts DC power to AC power. Why do I need them? If I'm building a transceiver, why do I need an oscillator? Why am I wasting your time talking about oscillators? Sorry? Deal with distortion. Not the answer I was having in mind. Okay. Suppose this device operates at a particular frequency. Does anyone remember roughly what frequencies that your cell phone operates at? Not modulation, it operates at a particular frequency, right? So the data is not transmitted DC, it's transmitted at a particular frequency, right? So you want to generate a carrier, so therefore you can put your data at a particular frequency. Okay. Can anyone very roughly draw me, I know you're all doing communication systems, all right, advanced communication systems, so you can't say to me, you don't know this. Okay, so how would you do that? Can someone tell me the basic structure of a transmitter, as an example? Okay, so we've got an air interface, we've got an amplifier, we've got an antenna, sorry. Okay, and here what do we usually have? We usually have the power amplifier. Alright. So in the first part of our course we talked about antennas. We talked about connecting these antennas using transmission lines, right? We didn't talk about switches or circulators, but generally if you want to use the same antenna, right, and what you would have is a TR switch, right? And you can think of a switch, this TR switch, to either you know, switches between the power amplifier being connected to the antenna so therefore it radiates, or it's connected to this low noise amplifier that we've just been talking about, right, and how to design these low noise amplifiers. We've been talking about how to design these power amplifiers, right? But these frequencies, we've been I mean, you can't assume that these are, we've been talking about 1 gigahertz, 5 gigahertz. Why have we been talking about that? Because usually that's the frequency which we want to transmit our signal at. Right? For example, if you're on your cellular phone, you're talking about, depending on which band, you can be 900 megahertz, you can be 1.3 gig, or you can be 1.8 gig. Right? Okay, so now you can think about it. We've got our digital chip, which generates signals, and for argument's sake, let's assume Will was terrible at designing his DACs and could only design DACs for us at 100 megahertz, or some value, some low number. So we had a DAC and we got an ADC. What's an ADC or a DAC? Does anyone know? Yeah, perfect. Yes. So we've got digital to analog and analog to digital. Okay. But the signal here, before we transmit it, we want to be transmitting it at, for argument's sake, say 2.4 gig. or 60 gig, right? So like we're at 60 gig, you know, you're at AMD and you're building these transceivers and they're operating at 60 gig, right? Because you're trying to get wireless VR. So this signal here has to be at 60 gig. The DAC is producing a signal, for argument's sake, say it's 800 megahertz. Okay? So how do I go from 800 megahertz to 60 gigahertz? Sorry? Modulate. How do I modulate it?
Mix with some carrier.
Mix. Okay. All right. So you got a mixer. Yes. And what does a mixer do?
So trace the original message signal.
Okay. Now, okay. So in the most simplest of forms, but it's never how it's implemented. It's not how it works in practice. When you're doing your advanced comms, usually what they assume is this mixer is actually a multiplication. So you go sine omega 1t multiplied by sine omega 2t. Suppose it's a sine omega 1, and this, you've got a signal in here, sine omega 2. When you multiply these two together, you get, if you remember your double angle formulae, it's, and I'm going to get this wrong, it's sine omega 1 plus sine omega 2 plus sine omega 1 minus omega 2. All right? And there's a half there or something. Okay? So essentially, in order to be able to get your signal to the frequency band that you want to transmit at, you need a mixer, but you also need this source, this oscillator. Right? Okay, this is what we're going to design now. This is what I'm showing you how to design, right? We're not, unfortunately, I don't have time. I'd love to go through the process of being able to design DACs and all that kind of stuff for you. Maybe next year if I, not in this course, maybe in a different course, we can actually talk briefly about it and we'll get some experts to come in and say, Stan, no, you're making mistakes. This isn't how you do it in real life. This is just how you do it in academia, but that's fine. So you've got a DAC. The DAC signal goes to the mixer. The mixer then takes it up into frequencies. Now, because you've got harmonics, here we're actually doing a product, right? But actually a mixer doesn't actually generate a product. What it actually does, it actually switches on it. You can actually think of it as switching a signal on and off. If you're switching a signal on and off, what does the spectrum look like? Or what do you get? If I had this function, right? If I had some signal and then I was putting this signal on and off, what do I get? Does anyone remember? You work out the Fourier series for this, right, because it's periodic, and then it just comes out as sine omega t plus sine omega 2t plus sine omega 3t plus blah, 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 right? So the point is, if you had when you build a real mixer, it doesn't actually just give you the fundamental, it gives you all these other harmonics. And then what you usually do is you put some kind of bandpass filter in here, and then you connect it up to your power amplifier. There's a whole bunch of other things that you need to do, but for the first little approximation, when you're designing a transmitter, this is what you would do. Right? And now what we're going to talk about is designing this oscillator. All right? Now, can you tell me anything about what do you think some of the characteristics, important characteristics for this oscillator are going to be? I'm not going to talk about it in this lecture. Hopefully I'll do it in the next lecture. But what do you think some of the important characteristics of this oscillator are? Frequency stability, right? And how would you also say, so frequency stability actually tells you, what does that mean to you?
Should be exactly at the frequency I want.
Right. Which it'll never be. Which it'll never be. No, being serious, right? And just so And why would it never be at exactly at the frequency that you want? Even though if it's there at 1 sec for a millisecond, or hundreds of a microsecond, why won't it be there all the time? Because there's noise, and also the filters that you can actually produce in order to give you that very narrow band. You can't produce infinitely thin filters. So what happens is this oscillator actually wobbles, right? So therefore, even though the frequency doesn't go far away, it still has something called phase noise. So therefore, what you actually see is you actually get a distribution of this thing, even though you've designed it to do this, to be a direct delta function at a particular frequency. Actually, what you actually do is when you connect it up to a spectrum analyzer, that's what you'll see, right? And then the other thing is, because in a real system, you can't also all the components. You can't, if you look up a data sheet, right, and for resistors or capacitors or inductors, or even if you're building them, the data sheet say plus or minus 1%, plus or minus 10%, right? So therefore, even though you think I've designed it for FO nominally, it's usually at some other frequency, F delta, right? So what do you usually do in order to get it back here? Or to convert it, to make sure that it's all right? Has anyone heard of phase lock loops? Yeah. All right, so so here what we need to do is, rather than just having an oscillator, we've got to put a phase lock loop around this oscillator before we feed it into the mixer. Okay. All right, so we've talked a little bit about microwave oscillators, and we said that oscillators, essentially what they do is they convert DC power to AC power. And essentially, the way that they do this is through this concept of a negative resistance device. And essentially, if you really think about it, what does negative resistance mean? It's really nothing more than amplification, but the amplification is done in such a way that the voltage and current are 180 degrees out of phase. Okay. Now, what we'll do is we'll go. I won't go through, poles and zeros and all this other stuff in order to show, and the Berkhausen conditions in order to make sure that you get the right phases in order to ensure that you've got sustained oscillations. All I'm going to do as part of this course is say, hey, you need to get this, and then I'll just leave it to you guys to go and look it up why that is the case, right? It's not part of this actual course, but really what you need to know is in order to be able to get that sustained oscillation, you need to have a negative resistance, and what you need to have is a phase difference between the voltage and current of 180 degrees in order for you to be able to get oscillation, right? So if you go through the process and work out the closed loop transfer functions and things like that, you'll be able to convince yourself that that's actually the case. All right, so and here what I'm doing is just actually showing you what negative resistance is, right? When I'm talking about the voltage and current being 180 degrees out of phase. Essentially all it is the voltage and the current. If I've got the voltage, the current is just minus the voltage divided by some constant. Okay. Now, the other thing is, there's also some important differences between when we're designing an oscillator versus an amplifier, right? Usually, an amplifier, even though it has gain, the other thing that's important about an amplifier is usually you have an input and you're amplifying that input. Whereas an oscillator, what you want is there to be a signal, irrespective of there being a signal at its input port, right? So you want it to be just generating, a signal, it oscillating, actually converting DC power to AC power. Always, okay. Now, the other thing that's important here is that in an oscillator, right, we've got some other things that we need to be aware of, which was in an amplifier, because the input and output reflection coefficients are generally less than 1, you can usually use a standard Smith chart, and that gives you everything that you need. In an oscillator, the situation gets a little bit more complex in the sense that your input and output reflection coefficients, usually you desire them to be greater than 1. And under those circumstances, you use a compressed Smith chart. And then there's also some slight differences that, in how you design your input and output matching networks. And here you're specifically trying to design your input and output reflection coefficients in an oscillator to be greater than 1. This is a little bit of terminology, a little bit of background, just trying to help you understand what we're trying to do here. Now, in order to avoid any confusion, what I'm doing is like what many books do, is they redefine the input and output matching networks and essentially call them generator tuning network and termination network. What is it? It's the input and output matching networks. Why am I calling it something different? So you don't confuse it with what's happening with an amplifier design. Same thing, we can easily call it input and output matching, but then for some of you might get confused. That's why I've decided to also follow what a lot of people use as terminology, which is, let's call it a generator and terminating network. Now, the thing that's important here is the generator tuning network determines the frequency of oscillation, whereas the terminating network, so this is an important point, right? And here I'm using the scattering matrix approach in order to be able to design this oscillator. But essentially what I'm saying is, if you're trying to design the frequency of oscillation, what controls the frequency of oscillation is actually the generator tuning network, which is also known as the input matching network, right? And the terminating network is the... Okay, fantastic. Now, this is just a little bit of information. I don't know how useful it is, but it's something worthwhile just knowing. Usually, this oscillation, once you've got this system and you've set it up, so you've set the amplifier, you've set up this oscillator, and you've put the how do you call it? You've set the conditions on the generator and the loading network so that it oscillates. But at time 0, it's stable. It's not actually oscillating. What gives it a little bit of a kick to actually start generating that oscillation? Well, generally it's just noise, right? Noise in the system builds up and it begins to oscillate. Now, that's all fine for most academic exercises, and that's what you would do. You just let it, give it a little bit of time and it would start to oscillate. But think of the situation where, hey, I've got my phone, I switch it on, and today, because it's a bit cold, it's taken 1 minute to start up. Tomorrow it's really hot and it started up immediately, right? So the point I'm making here is, if you're reading most texts, right, what they say is, the oscillation is triggered by, noise spikes and transients. That is true. If you give it sufficient time, that will happen, right? But generally what you do in these networks is you also build a startup circuit, which actually gives you, once you power up, you just give the system a kick, right? So therefore it actually starts oscillating, and and therefore it begins to oscillate, very, very microsecond after you've hit the power on switch, right? So therefore that's just a little bit of, I guess, engineering know-how or real world got to do when you're building a real system compared to when you read a textbook and the person who's written the textbook's probably never actually ever designed an oscillator in their life. Well, they say, well, yeah, it begins to oscillate, and you say, yeah, it does, but I want it to happen at a very deterministic, known time, and in order to do that, you will need a startup circuit. But notwithstanding that, yes, it's true. If the system's unstable and there's noise, it will begin to oscillate. You just don't know when it will occur. It might occur in a second, it might occur in a minute. But okay, so let's now look at this, and this is nothing more than the two-port configuration that we've usually been dealing with, and here all I'm doing is just defining the reflection coefficients of each of the points of the network, where I've got the generator tuning network, I've got the actual negative resistance device, and the terminating network. Now, before I move on to oscillation conditions, can anyone tell me some? And again, it's not in the lecture notes. So, but I just wanted to get a little bit of class engagement. Does anyone know or give me any examples of negative resistance devices? Have you ever seen one, used one, encountered one? You could say a tunnel diode. Anyway, all right. It's worthwhile. What I would do also, right, just have a look as maybe as a homework, a little bit of a homework exercise. Look up negative resistance devices and just look at some devices that can actually give you negative resistance. Right. Of course, we're going to use transistors in order to be able to give us some of these characteristics, but there are other devices that are out there which give you that negative resistance in order to build an oscillator. You don't need to actually always use a transistor, right? And you can actually use tunnel diodes. You can actually sometimes use vacuum tubes, and but usually tunnel diodes are fantastic because if you really want high power, high performance, oscillators. Tunnel diodes are phenomenally good in order to be able to do that. But why don't we use them in practice? Yeah, they're expensive. Will there wants to put them on his chip. He doesn't want to have an extra separate device because if you put it on your chip, you can make it cheap. Level of integration, etc., etc., etc. All right. Can I still have another 3 minutes? Because people always complain that I'm running a little bit late, and I am, and I'll finish at 10:02, so I've got 2 minutes now. Okay, so now let's talk about the oscillation conditions. And here what I've gone is talk about this two-port network. When can we guarantee that this two-port network oscillates? And in order to ensure that this two-port network oscillates, we need the following conditions, right? So therefore, the first being that the device has to be unstable, right? So we need the K to be less than 1. And then the other two conditions that are required are that the gamma in the input reflection coefficient multiplied by the generator reflection coefficient is exactly equal to 1, and the output port gamma out times gamma terminating network is equal to 1. And what I've done here for all of your benefits is actually just reminded you of these relationships, which are the relationships that we've actually gone through and derived for power amplifiers. They're exactly the same relationships, right? There's nothing different with them, except the only difference is instead of putting gamma L, I put gamma T. And instead of gamma S, I put gamma G, right? So gamma reflection coefficient at the terminating network, which is the same as the reflection coefficient at the load, I've just just replace that. You know, just so these are your standard. Oh, sorry, these bits here are your standard equations that you've used and love when you were doing your design for your power amplifiers. But there are also a couple of extra conditions, which is in order to ensure that we've got this instability, we need gamma in and gamma out to be greater than 1. Okay, let me finish there, and what we'll do in our next on Friday is go through the process of actually designing an oscillator. All right, so enjoy. And then the other thing that I've done for you all is I've actually downloaded and included in your notes this little tutorial on working with S parameters. And essentially what it does is, part of it you already know, right? Part of it is what's kappa, what's what are the stability circles and all that, and what's mu. I know that you know all that. But where it gets interesting is towards the end, of page 1, and then on page 2, where it specifically goes through the process of converting common source scattering parameters to either common drain or common gate. All right. So if you get a chance, just read through this. It's important. So therefore, at least you know that if someone gives you common source, and I'm going to actually, implement my, Colpitt's, Colpitt's oscillator, or, in common gate configuration, you can convert your scattering parameters from common source to common gate. Okay, so please, if you get a chance to have a look at this, it's interesting. It is really interesting stuff, and it's only 3 pages, so have a little bit of a read. Okay, and on that note, I'll speak to you on Friday. Will, can I grab you for a sec? Okay. All right, thank you. I was going to, I've got to go catch up with Robot. What's happening there?
I was in on one of the meetings, but she's quite a softly personality, and I think they're being honestly quite harsh with her. They brought her through, and then suddenly they said, "Here, 3 months, knock something together."
Yeah.
She's an MTS,
Yes.
equivalent to Gilbert.
Yeah.
Whereas with Gilbert, we all rallied round to help him out. Myself, Yin-Wan, Yuan, everybody.
Yeah.
And she's been left on her own to sort of sink or swim. And I'm not, as you can imagine, in a position to help her.
Yeah.
Really, I mean, I can talk to her about a sounding board, but I think she's had enough of the fighting,
Yes.
which I can understand. If the perception is everybody's against you, for your own sanity, you just have to do it.
Yeah. So that's what it seems like to me also.
I'm sure, but I am genuinely a bit upset. I'm upset that I think that she needs a lot more hand-holding, and that just simply isn't available. And, I think you have a question here that you...
Yeah, what 2 seconds? Yeah. Okay.
So I was reluctant to say to her, give it a go, kind of thing, stick it out.
Yeah. I can mix these all up. Oh well, I'll do that later. Yeah. Because I was going to go speak to her, and then look. I've seen everyone's reviews. And
we were talking about the internal. This is what she wrote about.
Yeah, performance reviews.
But hers was terrible. That's none of my business. But I thought,
Yeah. It was that, and then, but they want to take it to the next level.
But it seems to me that she's been set up too far. But then again, maybe that's just the way it works. It's like, well, when I don't want you anymore, I have to go through the motions of pretending that I'm being fair.
No, but it's not only what I was surprised about was can you give me a couple of minutes and we'll just do these? And then, okay. And, all right. She was next. She was actually next.
Okay,
Yes.
okay.
Yeah. All right, sorry.
Yeah.
It's okay. And we better get out of here before the whole.
Yes.
This one, the optimum input impedance, it's about the unilateral